What if you have to send a top secret message to your friend? Sounds easy, right? But what if your friend is halfway across the world and there are all sorts of spies trying to read that message? This is where cryptography comes in. Cryptography is a way of hiding messages by converting them into gobbledygook, or ciphertext. Only the person who knows the original method can translate it back. One of the earliest methods was Caesar's cipher. Caesar wanted to protect his military plans from falling into enemy hands, so he came up with a shifty method. He shifted each letter over by a predetermined number, say 3. That way, the message would appear meaningless. Once received, the general could shift each letter back by the same amount, revealing the original message. Problem is, people can compare the frequencies of letters in the encoded message to the fingerprint of the language, and therefore determine the original shift. Subsequent codes, like the Veneer cipher and the Enigma code, improved upon the Caesar cipher. All of these codes have one common problem. They require the sender and receiver to know the key beforehand. This won't work if you're trying to send secret messages to someone you've never met before. How would you share the secret key? In the 1970s, Whitfield Diffie and Martin Hellman came up with asymmetric cryptography, which requires 2 keys. Their protocol works like this. Alice has a secret message that she wants to share with Bob, but he's halfway across the world. How will she share her message across a public channel so that Eve, the eavesdropper, can't decipher it? Alice generates 2 large prime numbers, a private key, A, and a public key, G. Bob does the same, generating B, his large prime number, private key. I'll represent these with liquids. The first step in the protocol is to raise the public key to the powers of the private key. So Alice does this, getting G to the power of A. When Bob does this, he gets G to the power of B. Both of these are publicly known. I'll represent this by mixing the 2 colors. The final step in the protocol is for Alice to take Bob's exponential and raise it to her private key. Bob does the same. When Alice does this, she gets G to the B raised to the power of A, which is the same as G to the A times B. When Bob does this, he gets G to the A raised to the power of B, which is the same thing as G to the A times B. I'll represent this by mixing the colors. So she takes Bob's and raises it to her power, getting an ugly shade of brown. When Bob does the same, he gets the exact same shade of brown. But when Eve, the eavesdropper, tries to do this with what she knows, she can only get G to the power of A times G to the power of B, which is the same thing as G to the power of A plus B. Alice and Bob have successfully shared a secret without Eve knowing. Now you might think, when will I ever use this? I don't have any secrets. Think again. With the advent of the internet, we do everything online, from shopping to banking to applying to college. It is important to keep our private info safe and secure on the public internet. Diffie-Hellman protects your information from the Eves of the world.